So here's something that might surprise you. Quantum physics, this thing that sounds impossibly abstract, impossibly removed from your life, actually started with one of the most practical questions you can imagine. It started with light bulbs. Specifically, it started with people trying to figure out how to make better light bulbs, and in the process, they accidentally cracked open the door to a completely new understanding of reality. And once that door was open, there was no closing it again. But let's not get ahead of ourselves. Let's start where it actually began, which is the late 1800s. And to understand why quantum physics needed to exist at all, you have to understand what the world of physics looked like right before it showed up. Because here's the thing, by the end of the 19th century, most physicists thought they were basically done. Seriously, they thought the major work was finished. The universe, as far as they could tell, ran like a beautifully precise clock, and they had figured out how the gears worked. And honestly, you can't blame them for feeling that way. Isaac Newton had given them mechanics, the laws of motion, gravity, the way objects move and interact. James Clerk Maxwell had unified electricity and magnetism into one elegant set of equations and shown that light itself was an electromagnetic wave. Thermodynamics was well understood. The periodic table was filling in nicely. There was this famous sentiment, often attributed to Lord Kelvin, though historians debate whether he actually said it in exactly these words, that physics was essentially complete, with just a couple of small clouds on the horizon. 2 little puzzles left to clean up, and then the whole picture would be finished. Those 2 little clouds turned out to be hurricanes. One of them led to Einstein's theory of relativity. The other led to quantum mechanics. And together, they didn't just add a few new rooms to the house of physics. They burned the house down and built something entirely different in its place. So, let's talk about one of those clouds. Let's talk about the problem of hot things glowing. You've seen this your whole life. When you heat metal, think about a stovetop burner, or the coils inside a toaster, or a blacksmith heating iron. It starts to glow. First, it glows a dull red. Get it hotter, and it turns orange. Hotter still, and it goes yellow, then white. The color changes with temperature in a very specific, predictable way. And this wasn't just a curiosity. In the late 1800s, Germany was in an industrial boom, and companies like Siemens were manufacturing electric lighting. They needed to understand exactly how heated objects radiate light, because that knowledge would help them design more efficient bulbs. So the German Bureau of Standards was actively funding research into this question. The science was being driven, in part, by the light bulb industry, which is kind of wonderful when you think about it. Now, physicists had a concept they called a black body, and despite the name, it's not necessarily black. A black body is an idealized object that absorbs all the radiation that hits it, every wavelength, perfectly, and then re-emits that energy as thermal radiation. The spectrum of light it emits depends only on its temperature, nothing else, not what it's made of, not its shape, not its size, just temperature. And real objects approximate this behavior pretty well. That glowing iron in the forge is behaving roughly like a black body. The filament in an incandescent light bulb is behaving roughly like a black body. Even you, right now, lying there, are emitting thermal radiation, mostly in the infrared, which is why you show up on a thermal camera. You're a black body too, in a sense, a very low temperature one. So physicists wanted to write down an equation, a formula, that would predict exactly how much energy a black body radiates at each wavelength for a given temperature. plotted on a graph with wavelength on one axis and intensity on the other, and you get this characteristic curve, a hump that rises, peaks at some wavelength, and then falls off again. The peak shifts depending on temperature. For something at room temperature, the peak is way out in the infrared, invisible to your eyes. For the surface of the sun, around 5,500 degrees Celsius, the peak is right in the middle of the visible spectrum, which is not a coincidence. Our eyes evolved to be most sensitive to the wavelengths the sun puts out the most of. The shape of this curve was well measured by experimentalists. They had good data. The problem was that nobody could explain it. Nobody could derive that curve from the existing laws of physics. And this is where things get really interesting. Two physicists took a crack at it, and each got half the answer. Wilhelm Wien, a German physicist, came up with a formula in 1896 that worked beautifully for short wavelengths, the ultraviolet end of the spectrum, but fell apart at longer wavelengths. Then Lord Rayleigh and James Jeans, working from classical physics, derived a formula that worked well for long wavelengths, the infrared end, but gave completely insane predictions for short wavelengths. Their formula said that as you move toward shorter and shorter wavelengths, the energy radiated should increase without limit. A hot object should be blasting out infinite energy in the ultraviolet range. Infinite. Obviously, that doesn't happen. If it did, every warm object in the universe would be flooding space with lethal ultraviolet radiation. You couldn't light a candle without destroying the room. This absurd prediction was later given a wonderfully dramatic name, the ultraviolet catastrophe. And it wasn't a minor discrepancy. It was classical physics confidently predicting something that was laughably, catastrophically wrong. So you've got two formulas. One works on the left side of the curve. The other works on the right side. Neither works everywhere. And the laws of physics, as everyone understood them, could not produce the correct answer. Enter Max Planck. And I want you to know something about Planck because it matters for understanding what happened next. Max Planck was not a revolutionary by temperament. He was not someone who woke up wanting to overthrow the established order. He was, by all accounts, a deeply conservative physicist, methodical, careful, respectful of tradition. He believed in classical physics. He loved thermodynamics. When he was a young student and told one of his professors he wanted to study physics, the professor, Philipp von Jolly, actually tried to discourage him, saying that physics was essentially complete, that there was nothing important left to discover. Planck reportedly said he didn't want to discover new things. He just wanted to understand the existing foundations more deeply. That's the kind of person he was, which makes what he did next all the more remarkable because he didn't set out to start a revolution. He backed into one. In October of 1900, Planck was working on the black body problem, and he did something that was, at first, purely a mathematical trick. He found that he could get the right formula, one that matched the experimental data across the entire spectrum, at all wavelengths, if he made one strange assumption. He assumed that energy wasn't emitted continuously, like water flowing from a hose, but instead in tiny, discrete packets, little indivisible chunks. He called these chunks quanta, from the Latin word for how much, and the size of each quantum was determined by the frequency of the radiation, multiplied by a constant, a very, very small number that we now call Planck's constant, denoted by the letter h. Its value is approximately 6.626 times 10 to the negative 34 joule seconds. That's a decimal point followed by 33 zeros and then a 6. unimaginably small. Here's what that means in plain terms. Imagine you're on a ramp versus a staircase. Classical physics said energy was like a ramp. You could have any amount, any value, smoothly and continuously. Planck was saying no, energy is like a staircase. You can stand on this step or that step, but you can't stand between steps. Energy comes in specific amounts, and you can't subdivide it further than that. At everyday scales, the steps are so incredibly tiny that the staircase looks like a smooth ramp, which is why nobody had ever noticed. But at the atomic scale, the steps matter enormously. Now here's what's fascinating about Planck's state of mind. He didn't really believe this was physically true. He thought it was a mathematical trick, a clever workaround that happened to give the right answer. He expected that someone, eventually, would find a way to derive the same result using purely classical reasoning without this strange quantization business. He spent years trying to undo his own discovery, trying to find a way to get rid of the quanta and go back to continuous energy. He couldn't. Nobody could. And think about what that means. Think about what it feels like to be a deeply conservative, tradition-respecting physicist who has just, against every instinct, introduced an idea that undermines the foundation of everything you believe in. Planck later described the hypothesis as an act of desperation. He said he was willing to sacrifice any of his previous convictions about physics just to get a formula that worked. He didn't want to revolutionize physics. He wanted to solve a practical problem about how hot things glow. But the universe had other plans. The date matters here. December 14th, 1900. That's when Planck presented his derivation to the German Physical Society. And that date is often cited as the birthday of quantum physics. The whole thing started with a formula on a chalkboard in Berlin, presented by a man who wished it weren't necessary. But the quantum idea might have stayed a mathematical curiosity, a weird trick that worked but didn't mean anything deep, if it hadn't been for what happened 5 years later. In 1905, a 26-year-old patent clerk in Bern, Switzerland, picked up Planck's idea and did something far more radical with it. And this is where the story really starts to accelerate, because that patent clerk was Albert Einstein, and 1905 was the year he published not one, not two, but 4 papers that each would have been enough to make a career. Historians call it his annus mirabilis, his miracle year. And one of those papers was about light. Specifically, it was about something called the photoelectric effect. And this particular puzzle had been bugging physicists for over a decade. Here's what happens. You shine light on a metal surface, and sometimes electrons get knocked loose from the metal. That's the photoelectric effect. Light goes in, electrons come out. Simple enough. But the details were deeply weird, and classical physics could not explain them. See, if light is a wave, which Maxwell had convincingly shown it was, then the energy in a light beam depends on its intensity. A brighter beam carries more energy. So you'd expect that if you shine a really bright light on a metal, the electrons that get knocked out should be moving faster, because they've absorbed more energy. And if you dim the light way down, you might have to wait a while for enough energy to build up before an electron gets knocked loose. Makes sense, right? That's what wave physics predicts. But that's not what happens, not even close. What actually happens is that the speed of the ejected electrons depends on the color of the light, its frequency, not on the brightness. Shine dim ultraviolet light on the metal, and electrons pop out immediately, no waiting, moving at high speed. Shine an incredibly bright red light on the same metal, and nothing happens at all. no electrons. Zero. You can make that red light as blinding as you want, and you will never knock a single electron loose. The frequency is what matters, not the intensity. And the electrons come out instantly. There's no delay for energy to build up, which is what you'd expect if a wave were slowly depositing energy into the metal surface. Einstein looked at this and said something audacious. He said Planck's quanta weren't just a mathematical trick. Light actually comes in particles, discrete packets of energy, each one carrying an amount of energy equal to Planck's constant times the frequency. He called them light quanta. We'd later call them photons. And the photoelectric effect suddenly made perfect sense. Each photon hits one electron and either has enough energy to knock it free or it doesn't. The energy of each photon depends on the frequency. Red light has low-frequency photons, not enough energy per photon to free an electron, no matter how many of them you throw at the surface. Ultraviolet light has high-frequency photons, each one packing enough punch to liberate an electron on impact. Brighter light just means more photons, so more electrons get knocked out. But each individual electron still comes out with the same speed, because each individual photon carries the same energy. It was elegant, it was simple, and it was deeply, deeply troubling. Because Maxwell had proven that light was a wave. Interference experiments, diffraction patterns, polarization, mountains of evidence showed that light behaves as a wave, and now Einstein was saying it also behaves as a particle, not instead of a wave. Also, both, depending on how you look at it. This wasn't a minor philosophical quibble. Waves and particles are fundamentally different things. A wave is spread out, continuous, oscillating. A particle is localized, discrete, a little bullet of stuff. Saying something is both is like saying an animal is both a cat and a dog. Not sometimes one and sometimes the other, but somehow, genuinely, both at the same time. It doesn't make intuitive sense, and that discomfort you might be feeling right now, that sense that this can't quite be right, hold on to that. Because the physicists of the early 20th century felt exactly the same way. And the story of quantum mechanics, in many ways, is the story of people slowly, reluctantly, sometimes angrily, coming to terms with the fact that nature doesn't care whether its rules make intuitive sense to beings who evolved to track ripe fruit and avoid predators on the African savanna. But Einstein's paper on the photoelectric effect wasn't just philosophically important. It was practically important too. It's the reason solar panels work. When sunlight hits a photovoltaic cell, individual photons knock electrons loose in a semiconductor material, creating an electric current. That's the photoelectric effect, harnessed. Every solar panel on every rooftop on the planet is a direct technological descendant of Einstein's 1905 paper. He won the Nobel Prize for it in 1921, not for relativity, which is what most people assume, but for the photoelectric effect. The Nobel Committee was, in a sense, more comfortable rewarding a specific, well-confirmed result than the sweeping grandeur of relativity, which was still controversial in some quarters. So by 1905, you've got this strange situation. Energy is quantized. It comes in little packets. Light, which is definitely a wave, also behaves like it's made of particles. And the man who started the whole thing, Max Planck, still isn't entirely comfortable with where it's heading. Meanwhile, Einstein, who pushed the idea further than anyone, would eventually become one of quantum mechanics' most famous skeptics, spending decades arguing that the theory couldn't be the final word. The two people most responsible for launching quantum physics both had deep reservations about it. which tells you something about how strange this territory really is. But the quantum story was just getting started. Because if light, a thing everyone thought was a wave, could behave like a particle, then a young French physicist was about to ask the obvious next question. What if particles could behave like waves? And that question, when someone finally had the courage to take it seriously, would change everything. Because the man who asked it wasn't some seasoned professor with decades of research behind him. He was a graduate student writing his doctoral thesis. His name was Louis de Broglie, and his background was honestly a little unusual for a physicist. He came from French aristocracy. The de Broglie family held a dukedom, and Louis himself would eventually inherit the title. He'd actually started out studying history at the Sorbonne before switching to physics, partly inspired by his older brother Maurice, who worked in X-ray spectroscopy. And in 1924, at the age of 31, de Broglie submitted a PhD thesis that was so audacious, so seemingly out of left field, that his examiners didn't quite know what to do with it. Here's what he proposed. If light, which everyone had treated as a wave for over a century, could also behave like a particle, like Einstein showed with the photoelectric effect, then why couldn't the reverse be true? Why couldn't electrons, which everyone treated as particles, also behave like waves? It was a symmetry argument, really. Nature, de Broglie felt, ought to be consistent. If wave-particle duality applied to light, it should apply to matter too. And he didn't just wave his hands about it. He wrote down an equation. He said the wavelength of any particle is equal to Planck's constant divided by the particle's momentum. That's it. That's the whole formula. Wavelength equals h over mv, Planck's constant divided by mass times velocity. Simple, elegant, and completely wild. Think about what he was saying. You, sitting in a chair or lying in bed right now, you have a wavelength. Everything with mass and motion has a wavelength. A baseball flying through the air has a wavelength. A car on the highway has a wavelength. You, walking across a room, have a wavelength. The reason you've never noticed is that Planck's constant is absurdly tiny. It's 6.6 times 10 to the negative 34. So, for anything with everyday mass, the wavelength is so unimaginably small that it's completely undetectable. Your wavelength, walking at a normal pace, would be something like 10 to the negative 36 meters. That's trillions of times smaller than an atom. It's meaningless at human scales. But for an electron, which has almost no mass at all, the wavelength turns out to be on the order of the spacing between atoms in a crystal. And that's where things get real. De Broglie's thesis committee was, let's say, cautious. The story goes that his advisor, Paul Langevin, wasn't sure what to make of it and sent a copy to Einstein for his opinion. Einstein read it and reportedly said something along the lines of, "He has lifted a corner of the great veil." That endorsement was enough. De Broglie got his doctorate, and a few years later, in 1929, he won the Nobel Prize for it. A PhD thesis that won a Nobel Prize. That almost never happens. But here's the thing. A beautiful equation is just a beautiful equation until someone tests it. And the test came in a way that's actually a wonderful story about accidental discovery. In 1927, two American physicists at Bell Labs, Clinton Davison and Lester Germer, were shooting electrons at a nickel target, studying how the electrons scattered. During one experiment, the vacuum chamber broke. The nickel sample got oxidized, and to clean it, they heated it to high temperatures. What they didn't realize was that the heating process changed the nickel from a jumble of tiny crystals into a few large, well-ordered crystals. When they resumed the experiment, the scattering pattern completely changed. Instead of electrons bouncing off in all directions, they saw a distinct pattern of peaks and valleys, exactly the kind of pattern you'd expect if the electrons were behaving like waves diffracting off the regular rows of atoms in the crystal. It was an interference pattern, the same kind of pattern you get when water waves pass through two openings or when light waves pass through a diffraction grating. Except this was electrons. Particles, little bullets of matter, creating wave patterns. Davison and Germer measured the wavelength implied by the pattern, and it matched de Broglie's prediction almost exactly. Matter waves were real. An aristocratic French graduate student had been right. Electrons weren't just particles, they were also waves. And not in some vague metaphorical sense, in a precise, measurable, you can calculate the wavelength and it checks out sense. Now, you might be thinking, okay, so particles are waves and waves are particles. That's weird, but maybe it's just one of those things. Maybe at the quantum scale, everything is kind of both, and we just need to get used to it. And that's basically right, but the full implications of this are far stranger than they first appear. Because wave-particle duality isn't just a quirky fact about the quantum world. It leads directly to the single most famous and most baffling experiment in all of physics, the double-slit experiment. And this is where I want you to really settle in, because this experiment is the heart of quantum weirdness. Richard Feynman, who was one of the greatest physicists of the 20th century and also one of its best explainers, once said that the double-slit experiment contains the only mystery of quantum mechanics. He said, if you can understand this experiment, really understand it, you understand everything that's strange about the quantum world. And if you think you understand it without being disturbed by it, you haven't understood it. So let's walk through it slowly. The basic setup is simple. You have a barrier with two narrow slits in it, and beyond the barrier, you have a screen, something that will record where particles land. First, imagine doing this with something familiar, like paintballs. You shoot paintballs at the barrier, and some go through the left slit, some go through the right slit, and they hit the back screen. What pattern do you get? Pretty much what you'd expect. Two clusters of paint, one behind each slit. A little spread out, but basically two blobs. That's what particles do. Now do it with waves. Send water waves toward a barrier with two slits. Each slit becomes a new source of circular waves on the other side, and those two sets of waves overlap and interfere with each other. Where two wave crests meet, you get a bigger wave. Constructive interference. Where a crest meets a trough, they cancel out. Destructive interference. On the back wall, you get an interference pattern, alternating bands of high intensity and low intensity. Bright, dark, bright, dark. That's what waves do. Okay, now do it with electrons. Shoot electrons, one at a time, at a barrier with two slits. Each electron is a single particle. It hits the detector screen at a single point, making a tiny dot. So far, so particle-like. But here's the thing. If you keep shooting electrons, one by one, and you watch the pattern build up over time, dot by dot by dot, you don't get two blobs. You get an interference pattern, alternating bands of many hits and few hits, exactly like the wave pattern. Individual electrons, arriving one at a time, each one landing at a single point, collectively build up a wave interference pattern. Let that sink in for a moment. Each electron goes through the slits alone. There's no other electron for it to interfere with. And yet the pattern that emerges is unmistakably a wave interference pattern. It's as if each individual electron somehow passes through both slits simultaneously, interferes with itself, and then arrives at the screen at a single point. That's not an analogy. That's not a simplification. That's what the math says, and it's what the experiments show, over and over and over again, with electrons, with photons, with neutrons, even with molecules, hundreds of atoms large. But wait, it gets stranger. Because the natural next question is, okay, which slit does the electron actually go through? Let's just watch. Let's put a detector at one of the slits so we can tell which path the electron takes. And when you do that, when you set up any kind of measurement to determine which slit the electron passes through, the interference pattern disappears. You get two blobs instead. The simple act of observing which path the electron takes changes the outcome. When you don't look, you get a wave pattern. When you look, you get a particle pattern. This is not a flaw in the equipment. It's not that the detector is bumping the electron and messing things up, though that's a reasonable first guess. And physicists spent decades exploring that possibility. The result holds even in extraordinarily delicate experiments designed to minimize any physical disturbance. The act of acquiring information about which path the particle takes is what destroys the interference. It's about information itself, not about physical bumping. And this is where quantum mechanics starts to feel genuinely unsettling in a deep, philosophical way. Because it seems to be telling us that an electron doesn't have a definite path until something forces it to reveal one. Before measurement, it's not that the electron goes through the left slit or the right slit and we just don't know which. It's that the question, which slit, doesn't have an answer. The electron exists in what physicists call a superposition, a state that encompasses both possibilities simultaneously. And when a measurement is made, the superposition collapses into one definite outcome. This idea, superposition and its collapse upon measurement, became one of the central pillars of what's called the Copenhagen interpretation of quantum mechanics, developed primarily by Niels Bohr and Werner Heisenberg in the late 1920s. And to understand how they got there, and why it was so controversial, we need to talk about what was happening in theoretical physics during this incredibly fertile period between about 1925 and 1930, when a handful of young physicists, most of them barely out of their 20s, essentially built the mathematical framework of quantum mechanics from scratch. Because the double-slit experiment raises a question that demands a formal answer. If particles behave like waves, what exactly is waving? What is the wave equation for matter? And the person who answered that question was an Austrian physicist named Erwin Schrödinger. And the story of how he found his equation involves, among other things, a mysterious woman whose identity has never been confirmed. In late 1925, Schrödinger was a professor at the University of Zurich, 48 years old, which, in the world of quantum physics breakthroughs, made him practically ancient. Most of the people doing revolutionary work in this field were in their 20s. Heisenberg was 23 when he developed his version of quantum mechanics. Dirac was 23. Pauli was 25. And here was Schrödinger, a generation older, married, well-established, known more for his breadth of knowledge and his philosophical bent than for any single groundbreaking contribution. He was brilliant, no question, but he hadn't yet produced the kind of work that changes everything. That was about to change over Christmas. What we know is this. In December 1925, Schrödinger left Zurich for a holiday at a villa in the Swiss Alps, in the resort town of Arosa. He brought with him his ski gear, a couple of pearls to put in his ears to block out noise. He was very particular about working conditions, and the recent papers by Louis de Broglie on matter waves. He also brought a woman who was not his wife. We don't know who she was. Historians have tried to figure it out because Schrödinger kept detailed diaries of his romantic life. He had many affairs, openly, throughout his life, which caused no small amount of personal chaos. But this particular companion has never been identified. What we do know is that during this Alpine holiday, sometime between Christmas and the New Year, Schrödinger derived the wave equation for matter. The equation that would bear his name. The equation that is, to this day, the fundamental equation of non-relativistic quantum mechanics. Whatever else was happening in that villa, it was one of the most productive vacations in the history of science. So what did Schrödinger actually figure out? Let's think about this carefully, because his equation is the beating heart of quantum mechanics, and understanding what it says, even without the math, tells you something profound about the nature of reality. Here's the setup. De Broglie had said that particles have wavelengths. Davison and Germer had confirmed it experimentally. The double-slit experiment showed that particles really do behave like waves, producing interference patterns. But a wave needs an equation that describes how it moves and evolves over time. Think about waves on a string, or sound waves in air, or electromagnetic waves, Maxwell's equations. In classical physics, each type of wave has a wave equation, a mathematical rule that tells you how the wave propagates, how it changes shape, how it responds to forces. If matter behaves like a wave, there must be an equivalent equation for matter waves. That's what Schrödinger was after. And he found it. The Schrödinger equation is a differential equation. Don't worry about that term, it just means it describes how something changes, that takes as input the physical situation a particle is in. What forces are acting on it? Is it free, or is it trapped in a box, or is it orbiting an atomic nucleus? And it gives as output something called the wave function, usually written with the Greek letter psi. The wave function is a mathematical object that contains, in principle, everything there is to know about the quantum state of the particle. Now here's where it gets really interesting and really strange. When Schrödinger first derived his equation and started solving it for simple cases, like an electron orbiting a hydrogen atom, it worked beautifully, spectacularly, in fact. Remember how Bohr had proposed his model of the atom back in 1913, with electrons only allowed in certain orbits? Bohr's model worked for hydrogen, but couldn't handle anything more complex, and the rules about which orbits were allowed seemed arbitrary. He just postulated them. Schrödinger's equation derived those rules naturally. When you solve the equation for an electron in the electric field of a proton, the allowed energy levels just fall out of the mathematics. You don't have to assume them. They emerge because of the wave-like nature of the electron. Only certain standing wave patterns fit around the nucleus, the same way only certain frequencies resonate on a guitar string. The quantization that Bohr had to put in by hand, Schrödinger got for free. And not just the energy levels. The equation predicted the shapes of electron orbitals. Those strange, beautiful, sometimes dumbbell-shaped clouds you might have seen in chemistry textbooks. It predicted how atoms should behave in magnetic fields. It agreed with experiment after experiment. It was, by any measure, a triumph. But there was a problem, a deep, uncomfortable, philosophically maddening problem. And the problem was this: what is the wave function physically? What is psi? What is it that's waving? Schrödinger himself had a very clear idea of what he wanted it to be. He thought the wave function was a real, physical wave, that the electron literally was the wave, spread out in space, and that the particle picture was just an approximation. He imagined the electron as a wave packet, a localized bundle of wave energy, smeared out around the nucleus. This was a comforting picture. It was intuitive. It connected quantum mechanics back to the familiar world of classical waves. And it was wrong. Or at least, it couldn't be the whole story. The problem was pointed out most clearly by Max Born, a German physicist working in Göttingen, and his interpretation became one of the most consequential and most disturbing ideas in all of physics. Born proposed in 1926 that the wave function doesn't describe a physical wave at all. Instead, it describes probability. Specifically, the square of the wave function at any point in space gives you the probability of finding the particle at that point if you make a measurement, not where the particle is, where it might be found. The wave function is a probability wave. Think about what that means for a second. Before you measure the electron's position, it doesn't have a definite position. It has a probability distribution, a cloud of likelihood spread out in space. Some places are more probable than others. When you actually look, when you make a measurement, you find the electron at one specific spot, and the probability of finding it there was given by the wave function. But before you looked, it wasn't secretly at that spot all along. According to the standard interpretation, the question, "Where is the electron right now?" simply didn't have an answer before the measurement. Schrödinger hated this. He really, genuinely hated it. He had created the equation to restore some kind of classical, intuitive picture of the atom, and instead, his own equation was being used to support the idea that particles don't have definite properties until they're observed. He reportedly told Bohr, in frustration, that if he had known his equation would be used this way, he would never have gotten involved with quantum mechanics. He was only half joking. And this brings us to the great intellectual conflict that defined quantum physics in the late 1920s and beyond, a conflict between two camps, two philosophies, two ways of understanding what quantum mechanics was actually telling us about reality. On one side, you had the Copenhagen group, Niels Bohr in Denmark, Werner Heisenberg, Max Born, Wolfgang Pauli. These physicists accepted Born's probability interpretation and went further. They argued that quantum mechanics was complete, that it wasn't just our knowledge that was uncertain, but that nature itself was fundamentally probabilistic. An electron doesn't have a definite position before measurement, not because we're ignorant, but because there is no definite position to be had. Measurement doesn't reveal a pre-existing reality. It creates the reality. The act of observation brings a definite outcome into existence from a cloud of possibilities. On the other side, you had Einstein and Schrödinger, and a handful of others who felt this was deeply, fundamentally wrong. Not the math. Nobody disputed the math, the predictions, the experimental successes. What they disputed was the interpretation. Einstein's famous objection, which he expressed in various ways over many years, boiled down to this: he could not accept that God plays dice with the universe. He believed there must be a deeper, deterministic reality underlying quantum mechanics, hidden variables perhaps, that we simply hadn't discovered yet. The randomness, he felt, was a sign that the theory was incomplete, not that nature was fundamentally random. And here's where we need to talk about Heisenberg, because while Schrödinger was deriving his wave equation in the Alps, Heisenberg had already developed his own, completely different mathematical framework for quantum mechanics, and the rivalry between these two approaches is one of the great stories in physics. Werner Heisenberg was 23 years old in the summer of 1925, working as an assistant to Max Born in Göttingen. He suffered terribly from hay fever, and in June of that year his allergies got so bad that he retreated to Helgoland, a tiny, windswept island in the North Sea, essentially a bare rock with almost no pollen. And there, alone on this desolate island, with his face swollen from allergies, he had one of the most productive weeks in the history of theoretical physics. Heisenberg's approach was radically different from Schrödinger's. Where Schrödinger started with de Broglie's matter waves and tried to build a wave equation, Heisenberg started from a completely different philosophical position. He said, "We should only talk about things we can actually observe. We can observe the light that atoms emit, the spectral lines, the frequencies, the intensities. We cannot observe electron orbits inside atoms. So let's build a theory that deals only with observable quantities and the mathematical relationships between them." What he came up with was a formulation based on matrices, arrays of numbers arranged in rows and columns. Now, Heisenberg didn't actually know what matrices were when he started. He reinvented the mathematics from scratch, working out the rules for multiplying these arrays of numbers, and then discovered something bizarre. The order of multiplication mattered. If you multiplied quantity A by quantity B, you got a different answer than if you multiplied B by A. In normal arithmetic, 3 times 5 equals 5 times 3. In Heisenberg's quantum mechanics, the equivalent operation did not commute. A times B was not the same as B times A. This was strange and unsettling, and when Heisenberg showed his work to Max Born, Born immediately recognized what was going on. He told Heisenberg, "You've reinvented matrix algebra. The mathematics already existed. Heisenberg had just rediscovered it independently in the context of atomic physics. And that non-commutativity, that fact that the order of operations matters, turned out to be not a bug, but the most important feature. It was the mathematical expression of something that would become Heisenberg's most famous contribution to physics: the uncertainty principle. Here's the idea. In classical physics, you can, in principle, know both the position and the momentum of a particle simultaneously, with perfect precision. You can say exactly where a baseball is and exactly how fast it's moving at the same instant. In quantum mechanics, you cannot. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a limitation of your measuring instruments. It's not that your microscope isn't good enough or your detector is too clumsy. It's a fundamental feature of nature. The universe simply does not permit a particle to have both a perfectly definite position and a perfectly definite momentum at the same time. The uncertainty principle falls directly out of the mathematics, out of that non-commutativity that Heisenberg discovered on Helgoland. Position and momentum are what physicists call conjugate variables, and the product of their uncertainties can never be smaller than a specific tiny number related to Planck's constant. There it is again. Planck's constant, that same little h that showed up in black body radiation, in Einstein's photons, in de Broglie's matter waves. It keeps appearing, like a signature, every time quantum mechanics asserts itself. And here's a way to think about why the uncertainty principle makes intuitive sense, at least a little bit. Remember, particles have wave-like properties. Think about a wave. If you want a wave to have a very definite position, to be localized in one tiny spot, you need to add together many different wavelengths. A sharp spike in space is actually a combination of countless different waves superimposed. But wavelength is related to momentum through de Broglie's relation. So a particle with a very definite position is a superposition of many different momenta. its momentum is very uncertain. Conversely, a particle with a very definite momentum has a very definite wavelength, which means it's a nice, smooth, spread-out wave, and its position is completely uncertain. You can't have both at once. The wave nature of matter makes it impossible. Now, here's something important. Heisenberg's matrix mechanics and Schrödinger's wave mechanics looked completely different. They used different mathematics, different conceptual frameworks, different starting points. Heisenberg's was abstract, algebraic, dealing with arrays of numbers. Schrödinger's was visual, dealing with waves in space, solvable with familiar techniques from classical physics. Physicists initially split into camps. The older generation tended to prefer Schrödinger's approach. It felt more intuitive, more connected to physics they already knew. The younger generation, particularly those around Bohr and Born, gravitated toward Heisenberg. Schrödinger and Heisenberg personally disliked each other's work. Heisenberg called Schrödinger's wave mechanics disgusting in a letter to Pauli. Schrödinger found matrix mechanics repellent and abstract. But then, in 1926, Schrödinger himself proved something remarkable. The two formulations were mathematically equivalent. They were the same theory, expressed in different mathematical languages. Every prediction made by one could be derived from the other. It was like discovering that two books you thought were completely different stories were actually the same novel, one written in French and one in German. This was a stunning result, and it meant that the debates between the two camps weren't really about the physics. They were about interpretation, about what the mathematics meant. And that interpretive question, the question of what quantum mechanics is really telling us about the nature of reality, turned out to be far harder to resolve than anyone expected. In fact, it has never been fully resolved. Physicists argue about it to this day. But in the late 1920s, the most intense version of this argument played out between two towering figures, Niels Bohr and Albert Einstein. And their debates, which took place at a series of physics conferences between 1927 and 1930, are some of the most fascinating intellectual exchanges in the history of science. Because Einstein kept devising brilliant thought experiments designed to show that quantum mechanics was incomplete or inconsistent, and Bohr kept finding flaws in Einstein's arguments, often using Einstein's own theories against him. The most famous of these confrontations happened at the Fifth Solvay Conference in Brussels in October 1927. And to understand what was at stake, you need to picture the scene. 29 of the most brilliant physicists in the world gathered in a single room, 17 of them current or future Nobel Prize winners, and at the center of it all, two men arguing about whether reality exists when nobody is looking at it. That's really what they were arguing about. Einstein couldn't accept that a particle doesn't have a definite position until you measure it. That felt, to him, like giving up on the whole project of physics. The goal of physics, as Einstein saw it, was to describe what's actually out there, independent of whether anyone happens to be observing. The moon is there, whether or not you look at it. He actually said something very close to that once, asking a colleague if they really believed the moon only exists when someone observes it. And the Copenhagen interpretation, the view championed by Bohr and Heisenberg and Born, seemed to be saying something dangerously close to yes. Not about the moon exactly, but about electrons, photons, the fundamental constituents of matter. Before measurement, according to Copenhagen, asking where a particle is doesn't even have a meaningful answer. The particle isn't somewhere specific. It's in a superposition of many possible locations, described by the wave function, and only when you measure does one outcome become real. Einstein thought that was absurd. Not because he couldn't follow the math, he could follow it better than almost anyone alive, but because it violated his deepest intuitions about what a physical theory should do. So, at the Solvay conference in 1927, he started pushing back. And the way he did it was characteristically elegant. He didn't just wave his hands and say, "I don't like it." He constructed precise thought experiments, little imaginary setups designed to show that quantum mechanics led to contradictions, or that you could, in principle, beat the uncertainty principle and know both the position and momentum of a particle simultaneously. Here's one of the simpler ones he proposed. Imagine you have a screen with a single slit in it, and you shoot a particle through the slit. As the particle passes through, it diffracts. Its wave function spreads out, just like we talked about with the double-slit experiment. Now, behind the slit, there's a second screen, a detector screen, and the particle hits it somewhere. Einstein's argument went like this. When the particle hits the detector, you learn its position, but you also know it passed through the slit, which has a definite location. So you can figure out the particle's trajectory, and from that, you can calculate its momentum. And if you can know both position and momentum precisely, then the uncertainty principle is wrong, and quantum mechanics is incomplete. It sounds reasonable, right? But Bohr thought about it carefully and pointed out the flaw. The slit itself has a finite width. When the particle passes through it, the very act of confining it to that narrow region, pinning down its position, introduces uncertainty in its momentum because the wave diffracts. The narrower you make the slit to get a more precise position, the more the wave spreads out, and the less you know about which direction the particle is heading. The uncertainty principle holds. You can't beat it. Einstein came back the next day with a more sophisticated version, and Bohr refuted that one too. This went on, this back and forth, over breakfast, during conference sessions, in the hallways. The other physicists watched, fascinated. Paul Ehrenfest, who was friends with both men, reportedly said it was like watching a chess game, with Einstein proposing ever more ingenious gambits, and Bohr finding the defense each time. And then, at the next major Solvay conference in 1930, Einstein brought what he thought was his knockout punch. This one is beautiful in its cleverness. He imagined a box filled with radiation, photons bouncing around inside. The box has a shutter controlled by a clock. At a precise moment, the clock opens the shutter for just an instant and lets a single photon escape. Now, here's Einstein's argument. You can weigh the box before and after the photon escapes. Since energy and mass are related by his own equation, E equals mc squared, the tiny change in mass tells you the energy of the escaped photon precisely, and the clock tells you exactly when the photon left, so you know both the energy and the time of emission with arbitrary precision. But the uncertainty principle says there's a fundamental limit on how well you can know both energy and time simultaneously. It's the energy-time version of the uncertainty relation, analogous to the position-momentum one. So, if Einstein's thought experiment works, the uncertainty principle is violated. This one actually stumped Bohr. The story goes that Bohr was visibly shaken that evening. Leon Rosenfeld, who was there, recalled that Bohr went from one colleague to another, trying to work out a response, muttering, "It can't be true. It can't be true." He barely slept that night. But by the next morning, he had his answer, and it was devastating, because it used general relativity, Einstein's own masterpiece, against him. Here's what Bohr realized. When the photon leaves the box gets lighter. If you're weighing the box in a gravitational field, which you have to be, because that's how a scale works, then the change in mass causes the box to shift its position slightly in the gravitational field. And according to general relativity, a clock's ticking rate depends on its position in a gravitational field. Clocks run slower in stronger gravity, faster in weaker gravity. This is gravitational time dilation, a real effect that Einstein himself predicted. So the very act of precisely weighing the box, pinning down the photon's energy, introduces an unavoidable uncertainty in the position of the clock in the gravitational field, which introduces an uncertainty in the time measurement. When you work through the math carefully, the product of the energy uncertainty and the time uncertainty comes out to exactly Planck's constant, exactly what the uncertainty principle demands. Einstein's own theory of gravity saved quantum mechanics from Einstein's own attack. Think about that for a second. The irony is almost too perfect. And by all accounts, Einstein accepted Bohr's argument. He conceded that this particular thought experiment didn't work. And this is important. He didn't give up. He didn't suddenly decide that quantum mechanics was a complete description of reality. He just shifted his strategy. Instead of trying to show that quantum mechanics was internally inconsistent, he started arguing that it was incomplete, that there must be some deeper theory, some hidden layer of reality beneath the quantum description that would restore the determinism and definiteness he believed in. And this shift led to what might be the single most important thought experiment in the history of physics. It came in 1935, and it has a name you might have heard: the EPR paradox. EPR stands for Einstein, Podolsky, and Rosen. Albert Einstein, Boris Podolsky, and Nathan Rosen, who co-authored a paper that year with the somewhat dry title, "Can Quantum Mechanical Description of Physical Reality be Considered Complete?" Their answer, of course, was no. Here's the setup, and I want to walk through this slowly, because it touches on something genuinely strange, something that's going to matter a lot as we go deeper. Imagine you have a source that produces two particles at the same time, and these particles fly off in opposite directions. The particles are created in a special way so that their properties are correlated. For example, if you measure the spin of one particle and find it spinning one way, let's call it up, then you know instantly that the other particle's spin is down. This is a consequence of conservation laws, the same kind of thing that says if you break a stick in two, the pieces add up to the whole stick. The total spin has to be conserved. Now, according to quantum mechanics, before you measure either particle, neither one has a definite spin. They're both in superposition, both up and down at the same time. It's only when you measure one that it collapses into a definite state. And at that exact moment, the other particle, no matter how far away it is, also collapses into the opposite state. Einstein found this deeply troubling. Imagine the two particles have been flying apart for years. They're now on opposite sides of the galaxy. You measure particle A and find its spin up. Instantly, particle B becomes spin down. But how does particle B know? No signal could travel between them fast enough. Nothing travels faster than light. This seemed to require what Einstein mockingly called spooky action at a distance. And Einstein didn't believe in spooky action at a distance. He believed the particles must have had definite spins all along, from the moment they were created. The quantum mechanical description, which says they don't have definite spins until measured, must be missing something. there must be hidden variables, additional information that quantum mechanics doesn't capture, that determine the outcomes in advance. This is a completely reasonable position, by the way. If someone told you that two gloves were shipped in separate boxes to opposite sides of the world, and when you open one box and find a left glove, the other instantly becomes a right glove, you'd say that's ridiculous. They were always a left glove and a right glove. You just didn't know which was which until you looked. Einstein was essentially making the same argument. The particles carry their properties with them like hidden labels. Measurement just reveals the label. It doesn't create the reality. And for nearly 30 years, that seemed like a perfectly valid philosophical position. You could believe in hidden variables, or you could believe in Copenhagen, and there was no experiment that could tell the difference. It was a matter of taste, of interpretation, not of physics. The math made the same predictions either way, or so everyone thought. But then, in 1964, a quiet Irish physicist working at CERN named John Stuart Bell did something extraordinary. Bell was one of those people who thought deeply about the foundations of quantum mechanics at a time when most physicists considered such questions a waste of time. The prevailing attitude in physics departments was, shut up and calculate. Use the equations, get the right answers, and stop worrying about what it all means. Bell didn't accept that. He wanted to know what it all means. And he found a way to turn a philosophical debate into an experimental question. What Bell discovered was that if hidden variables exist, if the particles really do carry definite properties with them all, along the way Einstein believed, then there's a mathematical limit on how strongly the measurements of the two particles can be correlated. This limit is now called Bell's inequality. And here's the kicker. Quantum mechanics predicts correlations that violate Bell's inequality. The quantum predictions are stronger than anything hidden variables can account for, assuming the hidden variables are local, meaning they don't involve faster-than-light influences. So suddenly, you had a testable prediction. If you actually do the experiment, measure the correlations between entangled particles, and the correlations exceed Bell's limit, then local hidden variables are ruled out. Einstein's vision of a deeper, deterministic, locally realistic theory beneath quantum mechanics cannot be right. The universe really is as strange as Bohr said it was. Bell published his theorem in a relatively obscure journal, Physics Physique Physica, and for a while, not many people noticed. But the ones who did recognized it as a bombshell. The question was whether anyone could actually perform the experiment. And that challenge fell to experimentalists, people who could build the apparatus, generate entangled particles, and measure them with enough precision to test Bell's inequality. The first serious attempts came in the 1970s by John Clauser and Stuart Friedman at Berkeley, and their results favored quantum mechanics. But the definitive experiments, the ones that really closed the major loopholes, were performed by a French physicist named Alain Aspect in the early 1980s, working at the Institut d'Optique near Paris. Aspect's experiments were ingenious because he set them up so that the decision of what to measure on each particle was made after the particles were already in flight, too late for any signal traveling at the speed of light to carry information between the two detectors. That's the crucial part. Because if you imagine, even for a moment, that the particles are somehow secretly communicating, sending some kind of signal to coordinate their answers, well, that signal would need to travel faster than light to arrive in time. And since nothing travels faster than light, at least not according to everything we know about physics, that loophole gets slammed shut. Aspect's results were unambiguous. The correlations he measured violated Bell's inequality, and they did so by exactly the amount quantum mechanics predicted. Not a little more, not a little less. Exactly right. Now, let that settle in for a second. What this means, practically, is that the universe does not work the way Einstein hoped it would. There is no hidden layer of deterministic clockwork ticking away beneath quantum mechanics, at least not one that respects locality. The entangled particles are not carrying secret instructions. They genuinely do not have definite properties until they're measured. And when one is measured, the outcome of measuring the other one is instantly correlated, no matter how far apart they are. Not because a signal passes between them, but because they are described by a single quantum state that doesn't care about distance. And you might be thinking, okay, but if no signal passes between them, then this isn't really faster than light communication, right? And you'd be exactly right. That's one of the subtleties that trips people up. Entanglement does involve instantaneous correlations, but you can't use it to send a message. Here's why. When you measure your particle, you get a random result. Spin up or spin down, say. You can't control which one you get. It's genuinely random. Your partner, measuring the other particle far away, also gets a random result. It's only when you compare your results later, through ordinary communication, a phone call, an email, a letter carried by a pigeon, whatever, that you discover the correlations. The correlations are real, but they're hidden inside what looks like random noise until you bring the two data sets together, so no information travels faster than light. The universe protects its own speed limit, even while doing something that seems, on the face of it, completely impossible. This is one of those places where quantum mechanics asks you to update your intuition about what influence even means. Einstein called it spooky action at a distance. And honestly, that phrase has stuck around because it's perfect. It does feel spooky. But it's a real, experimentally confirmed feature of nature. Aspect's experiments were followed by many more, each one closing additional loopholes, getting more and more rigorous. In 2015, a team in the Netherlands, led by Ronald Hansen at Delft University of Technology, performed what's often called the first loophole-free Bell test. They closed the locality loophole, the detection loophole, and the freedom of choice loophole all in the same experiment. And the result was the same. Quantum mechanics wins. Bell's inequality is violated. Local hidden variables are out. So by the mid-1980s, and certainly by the 21st century, the debate that Einstein and Bohr started in the late 1920s had been settled experimentally. Not by philosophy, not by clever arguments, but by actual measurements in actual laboratories. And the answer was, Bohr was right. The universe is fundamentally probabilistic at the quantum level, and entangled particles exhibit correlations that no local realistic theory can explain. But here's the thing, and this is important, saying Bohr was right doesn't mean we fully understand what's going on. It means we know what the math predicts, and we know the predictions are correct. But the question of what quantum mechanics means, what it's really telling us about the nature of reality, that question is still very much alive. And this is where we get into the fascinating, sometimes maddening world of quantum interpretations. Let's talk about that for a second, because it's one of those topics that can keep physicists arguing late into the night, and it's surprisingly relevant to how you think about everything we've covered so far. The Copenhagen interpretation, the one Bohr and Heisenberg championed, says something like this: the wave function is a complete description of a quantum system, and when you make a measurement, the wave function collapses. It jumps from a superposition of many possibilities to one definite outcome. Before the measurement, the particle doesn't have a definite position or a definite spin. It's not that we don't know what it is. It genuinely doesn't have one. The measurement brings the property into existence. Now, Copenhagen was the dominant interpretation for decades, and in a practical sense, it works beautifully. Physicists use it every day. You set up your wave function. You evolve it according to Schrödinger's equation. And when you want to predict the outcome of a measurement, you calculate the probabilities using Born's rule. It's a recipe, and it gives the right answers. But it has this uncomfortable feature. It treats measurement as a special process, fundamentally different from everything else that happens in physics. The wave function evolves smoothly and deterministically according to Schrödinger's equation, until someone measures it, and then it suddenly, discontinuously collapses. And the theory doesn't really tell you what counts as a measurement. Is it when a photon hits a detector? When the detector sends a signal to a computer? When a human being looks at the computer screen? This is sometimes called the measurement problem, and it's been nagging at people since the very beginning. Schrödinger himself, remember, was deeply uncomfortable with this. That's actually the whole point of his famous cat thought experiment, which he proposed in 1935, the same year as the EPR paper. You've probably heard some version of this. You put a cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers, the vial breaks, and the cat dies. If the atom doesn't decay, the cat lives. According to quantum mechanics, until someone opens the box and looks, the atom is in a superposition of decayed and not decayed. And if you follow the logic rigorously, that means the cat is in a superposition of alive and dead. Schrödinger didn't propose this because he thought cats could actually be simultaneously alive and dead. He proposed it to show how absurd the Copenhagen interpretation becomes when you push it to macroscopic scales. It was meant as a reductio ad absurdum, a way of saying, look, something is clearly wrong or incomplete about this picture. And yet, here we are, almost 90 years later, and we still don't have a universally agreed upon resolution. What we do have are several competing interpretations, each of which handles the measurement problem differently, and each of which has passionate advocates. The most dramatic alternative is probably the many worlds interpretation proposed by Hugh Everett III in his 1957 doctoral thesis at Princeton. Everett was a remarkable character, brilliant, unconventional, and ultimately somewhat tragic. His idea was radical. What if the wave function never collapses? What if Schrödinger's equation is the whole story, and it applies to everything all the time, including observers, detectors, cats, and the entire universe? If you take that seriously, then when a measurement happens, the universe doesn't pick one outcome. Instead, it splits. In one branch, the atom decayed and the cat is dead. In another branch, the atom didn't decay and the cat is alive. Both branches are equally real. You, the observer, also split. One version of you sees a dead cat, another version sees a living cat. Each version is completely unaware of the other. Now, this sounds extravagant, maybe even crazy. You're multiplying entire universes every time a quantum event occurs. But mathematically, it's actually quite elegant. It takes the formalism of quantum mechanics completely at face value and doesn't add anything extra. No collapse, no special role for measurement. The price you pay is ontological. You have to accept that reality is incomprehensibly vast, an ever-branching tree of parallel worlds, most of which you'll never know about. Everett's thesis was supervised by John Wheeler, one of the most influential physicists of the 20th century, the man who coined the term black hole, among other things. Wheeler initially supported Everett's work, but the reception from the broader physics community was chilly. Bohr and his circle were unimpressed. The idea of splitting universes seemed like metaphysical excess, and Everett, discouraged, left academic physics entirely. He went into defense research, worked on operations research and computing, and never returned to physics. He died in 1982, at just 51, largely unrecognized for what many now consider one of the most important ideas in the foundations of quantum mechanics. It wasn't until the 1970s and 80s, when physicists like Bryce DeWitt championed the many worlds interpretation and gave it that catchy name, that it started gaining serious traction. Today, it's probably the second most popular interpretation after Copenhagen, and among cosmologists and quantum computing researchers, it might even be the most popular. But there are other paths through this thicket. One that's been gaining attention in recent decades is the decoherence program, which doesn't so much solve the measurement problem as dissolve part of it. The idea is this: when a quantum system interacts with its environment, and in practice, every macroscopic object is constantly interacting with air molecules, photons, vibrations, everything around it, the superposition doesn't disappear, but it becomes effectively invisible. The different branches of the superposition get entangled with the environment in a way that makes them unable to interfere with each other. It's as if the universe naturally sorts itself into distinct, non-overlapping stories, and within any one story, everything looks classical. You don't need to invoke a mysterious collapse. The environment does the work. Decoherence explains why we don't see cats in superpositions of alive and dead. The cat is interacting with so many particles in its environment, trillions upon trillions of air molecules, photons bouncing off its fur, that any quantum superposition gets smeared out into the environment almost instantaneously. The timescale for decoherence of a macroscopic object is absurdly short, something like 10 to the minus 40 seconds. That's so fast it might as well be instantaneous. So the quantum weirdness is still there, in principle, but it's been diluted into the environment so thoroughly that you could never detect it. Now, decoherence is a real physical process, and it's been confirmed experimentally. It's not an interpretation in the same way Copenhagen or many worlds are. It's more of a mechanism that any interpretation needs to account for. But it's been incredibly important for a field that emerged in the 1980s and 90s and has since become one of the most exciting areas of technology on the planet. And that field is quantum computing. Because if you want to build a computer that exploits superposition and entanglement, that uses qubits instead of classical bits, then decoherence is your mortal enemy. It's the thing that destroys your quantum information, that turns your delicate superpositions into ordinary classical states before you've had a chance to finish your computation. And that's the whole game, really. That's the central engineering challenge of quantum computing. How do you keep a qubit in superposition long enough to actually do something useful with it before the environment rushes in and ruins everything? So, let's talk about that. Let's talk about what a quantum computer actually does, why it's different from the machine you're using every day, and why building one has been one of the hardest engineering problems anyone has ever attempted. Start with a regular computer. A classical computer, as physicists like to call it. Everything it does, every email you send, every video you stream, every calculation it performs, comes down to bits, zeros and ones. A bit is either off or on, 0 or 1, and that's it. Your computer might have billions of transistors, each one acting as a tiny switch, and the arrangement of all those switches at any given moment represents the information the computer is working with. Simple in principle, staggeringly complex in practice, but fundamentally binary. Every bit has a definite value. A qubit is different. A qubit can be 0 or 1 or con, and here's where quantum mechanics walks through the door. A superposition of both. It can be in a state that's partly 0 and partly 1 simultaneously, with some probability amplitude for each. And if you have two qubits, they can be entangled so that their states are correlated in that deep, non-classical way we talked about earlier. Now here's what matters. If you have, say, 3 classical bits, they can represent one of 8 possible combinations at any given moment. 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. But 3 qubits in superposition can, in a sense, represent all 8 combinations at once. The quantum state encodes information about all of them simultaneously. And as you add more qubits, this grows exponentially. 10 qubits can hold information about 1,024 states simultaneously. 50 qubits, and you're dealing with over a quadrillion. Now, you might hear that and think, great, so a quantum computer just tries all the answers at once, right? It's like a massively parallel machine. And that's not quite right. It's a tempting picture, but it misses something crucial. You can't just read out all those superposed states. When you measure a qubit, you get one answer, 0 or 1. The superposition collapses, or decoheres, or branches, depending on your interpretation, but the practical result is the same. You get one classical outcome. So the trick of quantum computing isn't brute force parallelism. It's something more subtle and honestly more beautiful. It's about interference. Remember the double-slit experiment? How waves can interfere constructively and destructively, amplifying some outcomes and canceling others. That's exactly what a quantum algorithm does. It's designed so that the probability amplitudes for wrong answers interfere destructively. They cancel each other out, while the amplitudes for the right answer interfere constructively. By the time you measure, the right answer has been amplified and the wrong answers have been suppressed. It's not trying everything at once and picking the best one. It's choreographing the quantum waves so that the mathematics itself guides you toward the solution. And the person who first showed this could actually work in a way that would blow classical computers out of the water was a mathematician named Peter Shor. In 1994, Shor, working at Bell Labs, yes, the same Bell Labs where so much of 20th century physics and engineering happened, published an algorithm that could factor large numbers exponentially faster than any known classical algorithm. And that might sound abstract, but here's why it sent shockwaves through the worlds of both physics and computer science. The entire security infrastructure of the internet relies on the fact that factoring large numbers is hard. RSA encryption, the system that protects your bank transactions, your passwords, your private communications, is built on the assumption that if you multiply two very large prime numbers together, it's practically impossible to figure out what those original primes were, at least with a classical computer. A number with a few hundred digits? It would take the best supercomputers longer than the age of the universe to factor it. But Shor's algorithm, running on a sufficiently powerful quantum computer, could do it in hours, maybe minutes. Now, when Schrödinger published this, there was no quantum computer that could run his algorithm on anything meaningful. The largest quantum computations at the time involved a handful of qubits at best. But the theoretical result was electrifying. It proved that quantum computers weren't just a curiosity. They could solve problems that classical computers fundamentally couldn't, at least not in any reasonable amount of time. And it gave the entire field a concrete, urgent goal. But here's the thing, and this is where the engineering story gets really dramatic. Building a quantum computer that can actually run Shor's algorithm on a large number requires thousands, maybe millions of qubits, all maintaining coherence long enough to complete the calculation. And in the mid-90s, people could barely keep a single qubit coherent for more than a few microseconds. The gap between theory and reality was enormous. It was like knowing the aerodynamic equations for a supersonic jet in 1850. Beautiful math, no way to build it. So how do you keep qubits coherent? That's been the defining question. And different groups have pursued radically different physical systems to try to answer it. Some use trapped ions, individual atoms suspended in electromagnetic fields in a vacuum, manipulated with laser pulses. The qubit is encoded in the energy levels of the atom, and because the atom is isolated in a vacuum, it's relatively well protected from environmental noise. Trapped ion systems have achieved some of the longest coherence times and highest gate fidelities of any platform. Groups at the University of Innsbruck, the National Institute of Standards and Technology in Boulder, and companies like IonQ and Quantinuum have pushed this approach remarkably far. Others use superconducting circuits, tiny loops of superconducting metal cooled to temperatures colder than outer space, around 15 millikelvin, just a hair above absolute zero. At those temperatures, electrical resistance vanishes, and the circuit can sustain quantum states. The qubit is essentially an artificial atom, an electrical circuit that behaves quantum mechanically. This is the approach Google and IBM have championed. In 2019, Google's team, led by John Martinez, announced that their 53-qubit processor, called Sycamore, had achieved what they called quantum supremacy. It performed a specific calculation in about 200 seconds that they estimated would take the most powerful classical supercomputer 10,000 years. Now, IBM pushed back on that claim, arguing their classical supercomputer could do it in a matter of days, with clever programming, not 10,000 years. The debate got heated, but even the most conservative reading of that result showed that quantum computers were starting to enter territory where they could do things classical machines genuinely struggled with. And then there are more exotic approaches. Photonic quantum computing, where qubits are encoded in properties of individual photons, their polarization, their path, their arrival time. The Canadian company Xanadu has been pursuing this. There's topological quantum computing, which Microsoft has bet heavily on, based on exotic quasi-particles called anyons that theoretically store quantum information in a way that's inherently protected from local disturbances. The idea is gorgeous. Instead of fighting decoherence head-on, you encode information in global topological properties that local noise can't easily disrupt. It's like tying a knot in a rope. You can jiggle the rope all you want, but the knot stays. The catch is that the specific anyons you need, non-abelian anyons, have been extraordinarily difficult to create and verify in the lab. Microsoft announced evidence for them in a 2018 paper that was later retracted due to data issues, which was a significant setback. They've since published new results, but the topological approach remains the most speculative of the major platforms. Here's what's really clever about all of this, though. While engineers have been working to make better physical qubits, theorists discovered something remarkable in the mid-90s that changed the entire outlook for the field. It's called quantum error correction, and it was developed independently by Peter Shor, yes, the same Shor, and Andrew Steen around 1995 and 96. The basic idea is that you can encode one logical qubit across many physical qubits in such a way that errors can be detected and corrected without ever measuring the actual quantum information. Think about that for a second. In classical computing, error correction is straightforward. You just copy the bit and check the copies. But in quantum mechanics, you can't copy a quantum state. There's actually a theorem about this, the no-cloning theorem, proved by Wouters and Zurek in 1982. You cannot make a perfect copy of an unknown quantum state. So quantum error correction has to work differently. It spreads the information across entangled qubits in a way that lets you detect whether an error has occurred, a bit flip, a phase flip, without learning what the actual quantum state is. It's one of the most ingenious theoretical constructions in all of computer science. The practical implication is profound. It means that even if your physical qubits are noisy and error-prone, as long as the error rate is below a certain threshold, and this threshold has been calculated to be around 1% or so for many error-correcting codes, you can, in principle, perform arbitrarily long quantum computations reliably. You just need enough physical qubits to encode each logical qubit. And enough might mean 1,000 physical qubits per logical qubit, or even more, depending on the error rates and the code you're using. That's why the roadmaps from companies like IBM and Google talk about building machines with millions of physical qubits. Not because you need millions of qubits for the algorithm itself, but because most of them are dedicated to error correction, to keeping the quantum information alive and accurate while the computation unfolds. And this is where the field stands right now, in this fascinating, frustrating, exhilarating middle period. We have quantum computers that work. They're real. You can access some of them over the cloud. IBM has made several of its quantum processors available to anyone who wants to experiment. But the machines we have today are what researchers call NISQ devices, noisy, intermediate-scale quantum. They have tens to a few thousand qubits, but those qubits are noisy. The error rates are still significant, and we don't yet have full fault-tolerant error correction running at scale. They can do interesting things that push the boundaries of what classical computers handle easily, but they can't yet run Shor's algorithm on numbers large enough to threaten encryption, and they can't yet simulate complex molecules with the precision that would revolutionize drug discovery or material science. But the trajectory is remarkable. Coherence times have improved by orders of magnitude over the past 2 decades. Gate fidelities, the accuracy of individual quantum operations, have climbed above 99% in several platforms. And in 2023, a team at Harvard and MIT, working with the startup Quera, demonstrated 48 logical qubits with error correction using a system of neutral atoms held in optical tweezers, which was a genuine milestone. The pieces are coming together, just slowly, painstakingly, the way all great engineering challenges unfold. And quantum computing is only one branch of a broader quantum technology revolution that's been building. there's quantum sensing, where the extreme sensitivity of quantum states to their environment, the very thing that makes decoherence such a problem for computing, becomes an advantage. If a qubit is exquisitely sensitive to magnetic fields, or gravitational gradients, or temperature fluctuations, you can use it as an incredibly precise sensor. Atomic clocks, which are already the most accurate timekeeping devices ever built, are quantum sensors, and next-generation quantum sensors could detect underground structures, monitor brain activity with unprecedented resolution, or improve GPS accuracy by orders of magnitude. And then there's quantum communication, which brings us back to entanglement in a way that feels almost poetic. Because here's the thing about entanglement that we've been building toward. You can't use it to send a message faster than light. We talked about that. But you can use it to make communication fundamentally, provably secure. And that idea, quantum communication, is one of the most beautiful applications to come out of all the strangeness we've been exploring together. Let me walk you through how it works, because it's genuinely clever. The core protocol is called quantum key distribution, and the most famous version of it was proposed in 1984 by Charles Bennett at IBM and Gilles Brassard at the Université de Montréal. It's known as BB84, after their initials in the year. And the basic idea is this. Instead of using entanglement directly, it uses the fact that measuring a quantum state disturbs it. Remember Heisenberg's uncertainty principle? How observing a quantum system inevitably changes it? That's not a bug here. That's the entire security mechanism. Imagine you want to send a secret key to someone, a string of ones and zeros that you'll both use to encrypt and decrypt messages. In classical communication, the problem is always the same. How do you share that key without someone intercepting it? If an eavesdropper copies the key in transit, they can read everything, and you'd never know. But with quantum key distribution, you encode each bit of the key onto the quantum state of a photon, its polarization, say. And here's what makes it work. If anyone intercepts that photon and measures it, they disturb its state. They can't copy it perfectly because of the no-cloning theorem. Remember Wouters and Zurek from 1982. They can't even measure it without altering it. So when you and your intended recipient compare notes afterward, and there's a specific procedure for doing this over a normal, public channel, you can detect whether anyone was listening in. If the error rate in your shared key is above a certain threshold, you know someone was tampering, and you throw the key away and start over. If the error rate is low, you can be confident the key is secure, and you use it. Think about what that means. It's not security based on the difficulty of a math problem, like RSA encryption, which we know a sufficiently powerful quantum computer could break. It's security based on the laws of physics. An eavesdropper isn't just unlikely to succeed. They physically cannot succeed without leaving evidence. That's a fundamentally different kind of security guarantee. Now Bennett and Brassard's BB84 protocol used individual photon polarization states, not entanglement. But in 1991, Arthur Eckert, who was then a doctoral student at Oxford, proposed a different scheme, called E91, that does use entangled photon pairs. In Eckert's protocol, a source generates pairs of entangled photons and sends one to each party. They each measure their photons using randomly chosen measurement settings, and then they compare a subset of their results. Because of Bell's inequality, the very thing John Bell worked out back in 1964, the thing Clauser and Aspect tested, they can verify that their photons were genuinely entangled. And if they were genuinely entangled, no eavesdropper could have intercepted and measured one of the photons without breaking the entanglement and introducing detectable errors. It's Bell's theorem repurposed as a security check. That's just gorgeous, honestly. An idea born from a philosophical debate about whether quantum mechanics was complete, Einstein's old complaint, turned into a practical technology for unbreakable encryption. And this isn't just theoretical anymore. Quantum key distribution systems are commercially available today. Companies like ID Quantique in Geneva have been selling them since the mid-2000s. Banks have used them. Government agencies have tested them. In 2017, China launched a satellite called Mitius, named after an ancient Chinese philosopher, and used it to distribute entangled photon pairs between ground stations separated by over 1,000 kilometers. The team, led by Jianwei Pan at the University of Science and Technology of China, demonstrated both quantum key distribution from space and entanglement distribution over record-breaking distances. They even conducted a quantum-secured video call between Beijing and Vienna, using keys distributed partly through the satellite and partly through fiber optic links. That was a real milestone, the first intercontinental quantum-secured communication. But here's where the engineering challenges come in, and they're significant. Photons are fragile messengers. When you send a single photon through an optical fiber, it can get absorbed or scattered. Over short distances, say 100 kilometers or so, this is manageable. But over longer distances, you lose too many photons, and the key distribution rate drops to practically nothing. In classical communication, you solve this with repeaters, devices that amplify the signal along the way. But you can't amplify a quantum signal without measuring it, and measuring it destroys the quantum information. The no-cloning theorem strikes again. So researchers have been working on something called a quantum repeater, which is a much more sophisticated device. Instead of amplifying the signal, a quantum repeater uses entanglement swapping, a technique where you create entanglement between two particles that have never directly interacted by using intermediate entangled pairs and Bell state measurements. You essentially chain together short entangled links into one long entangled link. It's like building a bridge across a wide river by first building shorter spans between pylons. Each span is manageable on its own, and the entanglement swapping protocol connects them into a continuous quantum channel. The catch is that quantum repeaters require quantum memory, the ability to store a quantum state reliably while you wait for the other links in the chain to be established. And quantum memory, as you might guess by now, runs straight into the decoherence problem. You need to hold a delicate quantum state for milliseconds, maybe even seconds, while classical signals coordinate the swapping process. That's an eternity in quantum terms. Teams around the world, at Delft, at Harvard, at various Chinese institutions, have demonstrated prototype quantum repeater nodes. But a full, practical, long-distance quantum repeater network doesn't exist yet. It's one of the grand challenges of the field. And this connects to an even bigger vision: a quantum internet. Not a replacement for the regular internet. You'd still stream your shows and send your emails over classical networks. But a parallel quantum network that could distribute entanglement on demand between any two nodes. You could use it for quantum key distribution over arbitrary distances, obviously. But you could also use it to connect quantum computers together, creating distributed quantum computing systems more powerful than any single machine. Or you could use it for quantum sensor networks, where entanglement between distant sensors improves their collective precision beyond what any individual sensor could achieve. The European Union has a major initiative called the Quantum Internet Alliance, working toward exactly this. China has built the world's longest quantum communication backbone, a fiber optic link running over 2,000 kilometers from Beijing to Shanghai, with trusted relay nodes along the way. It's not a full quantum repeater network yet. Those trusted nodes are a compromise, a classical weak point. But it's a real, functioning infrastructure that's being used for secure government and financial communications right now. So let's step back for a moment and appreciate where we've arrived. We started this whole journey with Max Planck reluctantly introducing a mathematical trick to explain how hot objects glow. And now we're talking about satellite-based entanglement distribution and the architecture of a future quantum internet. Every step along the way, Einstein's photons, de Broglie's matter waves, Heisenberg's uncertainty, Bohr and Einstein arguing in hotel lobbies, Bell scribbling inequalities that nobody paid attention to for years, Aspect running his experiments in a basement in Orsay, teams in Delft closing the last loopholes. Every single one of those steps was necessary to get here. The technology we're building now is a direct consequence of people refusing to stop asking what quantum mechanics actually means. And there's one more piece of this story that I want to share with you, because it ties together so many of the threads we've been following. It's about what happens when you push quantum mechanics to its absolute limits, not in a lab, not in a computer, but in our understanding of reality itself. Because even now, even after all the experiments and all the engineering breakthroughs, there are questions at the foundations of quantum mechanics that remain genuinely open. Questions that the smartest people in physics disagree about. And some of those questions have started to intersect with other deep mysteries. The nature of gravity, the structure of space-time, the very deepest limits of what physics can tell us about the universe. And honestly, this might be the most fascinating part of the whole story. So here's the situation. Quantum mechanics, as a theory, is spectacularly successful. It predicts the outcomes of experiments to absurd levels of precision. Remember, the magnetic moment of the electron, quantum electrodynamics predicts it to something like 10 decimal places, and experiments confirm every single one. No other theory in the history of science has been tested so thoroughly and passed so consistently. And yet, there's this enormous gap in our understanding, and it has to do with gravity. Think about what we know. We have quantum mechanics, which governs the very small, atoms, photons, electrons, all the stuff we've been talking about. And we have general relativity, Einstein's other great theory, the one he published in 1915, which governs gravity and the very large, planets, stars, galaxies, the expansion of the universe itself. General relativity tells us that gravity isn't really a force in the usual sense. It's the curvature of space-time. Massive objects bend the fabric of space and time around them, and other objects follow those curves. It's a beautiful, geometric theory, and it's been confirmed over and over. GPS satellites have to account for general relativistic time dilation, or your phone's map would drift by kilometers within a day. That's how real this is. Now here's the problem. These two theories, quantum mechanics and general relativity, are each incredibly successful in their own domain. But they don't talk to each other. They're built on fundamentally different assumptions about how the universe works. In quantum mechanics, particles exist in superpositions. Measurements are probabilistic, and the observer plays this strange central role. In general relativity, space-time is smooth, continuous, deterministic, a classical stage on which the drama of the cosmos plays out. When you try to combine them, when you try to write down a quantum theory of gravity, the way we have quantum theories of electromagnetism and the nuclear forces, the math breaks. You get infinities. Not the kind of infinities you can tame with clever mathematical tricks. Physicists actually have a whole toolkit for dealing with certain kinds of infinities, a process called renormalization that works beautifully for the other forces. But gravity resists. When you try to quantize gravity the same way, the infinities multiply and pile up, and the theory becomes meaningless. It predicts nothing. This isn't just an abstract mathematical headache. It means there are real physical situations where we literally don't know what happens. The center of a black hole, for instance. General relativity predicts that a collapsing star can form a singularity, a point of infinite density where space-time curvature becomes infinite. But infinite in physics usually means your theory has broken down, that you've pushed it past its limits. Most physicists believe that if we had a proper quantum theory of gravity, it would resolve that singularity, replace it with something finite and comprehensible. But we don't have that theory yet. The same goes for the very earliest moments of the Big Bang. Wind the clock back far enough, and you reach a point where the entire observable universe was compressed into a region so small that quantum effects and gravitational effects were both important simultaneously. That's the regime where we need both theories to work together. And right now, we can't make them do that. So people have been trying for decades, and the approaches they've come up with are some of the most ambitious intellectual constructions in the history of physics. The most famous attempt is string theory. The basic idea emerged in the late 1960s and early 1970s, originally in a completely different context. People were trying to understand the strong nuclear force. But by the mid-1970s, physicists like John Schwartz and Joel Shirk realized that string theory naturally included a massless spin 2 particle that behaved exactly like the graviton, the hypothetical quantum carrier of gravity. That was a stunning surprise. The theory wasn't designed to include gravity. Gravity just showed up, uninvited, as a natural consequence of the mathematics. The core idea is that the fundamental constituents of nature aren't point particles. They're tiny, one-dimensional vibrating strings. Different vibrational modes of the string correspond to different particles, the way different vibrational modes of a guitar string produce different notes. One mode gives you an electron, another gives you a photon, another gives you the graviton. It's an elegant picture, but it comes with baggage. For the math to work consistently, string theory requires extra spatial dimensions, 6 or 7 beyond the 3 we experience. These extra dimensions would be curled up incredibly small, far too small to detect directly. And the number of ways they can be curled up is astronomical. Estimates suggest something like 10 to the 500 possible configurations, each corresponding to a different possible universe with different physical laws. That's such an incomprehensibly large number that some physicists see it as a feature. Maybe our universe is just one possibility in a vast landscape, while others see it as a sign that the theory has lost its predictive power. String theory has produced beautiful mathematics. It's led to deep insights in pure math, in the study of black holes, in our understanding of certain strongly interacting quantum systems. But after more than 40 years of intense work, it hasn't produced a single prediction that's been tested and confirmed by experiment. That's not necessarily a death sentence for the theory. The energy scales where stringy effects would become visible are so far beyond what any conceivable particle accelerator could reach that direct tests may simply be impossible with current technology. But it does mean that string theory occupies this unusual position in physics, widely studied, deeply influential, but empirically unconfirmed. There's another major approach called loop quantum gravity, championed by physicists like Abhay Ashtekar, Carlo Rovelli, and Lee Smolin, starting in the mid-1980s. Loop quantum gravity takes a very different philosophical stance. Instead of starting with strings and hoping gravity emerges, it starts with general relativity and tries to quantize it directly. The key insight is that space itself might be quantized, not smooth and continuous, but made up of discrete chunks at the tiniest scales. The theory predicts that area and volume come in discrete units, like energy levels in an atom. The smallest possible area would be roughly on the order of the Planck length squared, and the Planck length is about 10 to the minus 35 meters, which is so small that if an atom were blown up to the size of the observable universe, the Planck length would still be smaller than a single atom in the original unscaled world. That's the scale we're talking about. It's almost absurdly tiny. Loop quantum gravity has its own successes and its own problems. It naturally resolves the singularity at the center of a black hole and at the Big Bang. Replace the singularity with a bounce, a moment of extremely high but finite density. But it has trouble reproducing the smooth space-time of general relativity at large scales, and it doesn't naturally unify gravity with the other forces the way string theory aspires to. And here's what I find really beautiful about this whole situation. These open questions about quantum gravity aren't just technical puzzles for specialists. They connect back to the foundational questions about quantum mechanics that we've been discussing all along. Remember the measurement problem? The question of what actually happens when you make a measurement, why the wave function seems to collapse. Some physicists, Roger Penrose is the most prominent, have suggested that gravity might be the answer. Penrose has argued since the 1990s that when a quantum superposition involves objects massive enough to significantly curve spacetime in different ways, nature can't sustain the superposition. The conflict between the two different spacetime geometries forces a collapse, not because of any observer, not because of decoherence in the usual sense, but because of gravity itself. He calls it objective reduction. It's a testable idea, at least in principle, and there are experiments being designed right now to look for it. Experiments that would put small masses into quantum superpositions and check whether they collapse faster than standard quantum mechanics predicts. Think about what that would mean. If Penrose is right, then the measurement problem, the thing that's been bugging physicists since the 1920s, the thing Bohr and Einstein argued about, the thing that spawned the Copenhagen interpretation and the many worlds interpretation and all the rest, would be resolved by gravity. The two great unsolved problems of fundamental physics would turn out to be the same problem. That's the kind of possibility that keeps theoretical physicists awake at night, in the best possible way. And there's more. In 2019, a thought experiment called the Wigner's friend scenario was pushed to its logical extreme by Daniela Frauchiger and Renato Renner at ETH Zurich. They showed that if you take quantum mechanics seriously and apply it to observers who are themselves being observed by other observers, you can derive contradictions. Situations where different observers, each applying the rules of quantum mechanics correctly, reach incompatible conclusions about what happened. It's Schrödinger's cat all over again, but sharper, more rigorous, harder to dismiss. The result doesn't tell us which interpretation is right, but it does suggest that something in our current understanding has to give. Either quantum mechanics needs to be modified, or our assumptions about what it means to be an observer need to be revised, or the idea that experimental results are objective facts that everyone can agree on needs to be abandoned. Each of those options is radical. Now, you might be thinking, does any of this matter for everyday life? And the honest answer is, not yet, not directly. But that's what people said about quantum mechanics itself 100 years ago. When Planck introduced his constant in 1900, nobody could have predicted lasers, transistors, MRI machines, or quantum computers. When Bell wrote his inequality in 1964, nobody imagined it would lead to quantum cryptography and satellite-based entanglement distribution. The history of physics is full of moments where the most abstract, seemingly useless foundational work turned out to be the seed of transformative technology decades later. And in the meantime, the practical quantum revolution is already happening. The quantum sensors we touched on earlier are being developed for medical imaging, for navigation systems that work without GPS, for geological surveys that can detect mineral deposits or underground structures. Quantum computers, even in their current noisy, imperfect state, are being explored for drug discovery, materials science, financial modeling, optimization problems in logistics. Quantum communication networks are being built and tested right now, laying the groundwork for a future where information security is guaranteed not by the difficulty of a math problem, but by the laws of physics themselves. And all of it, every single piece of it, traces back to those early days, to Planck's reluctant quantization, to Einstein sitting in the patent office thinking about light, to de Broglie writing a PhD thesis that his examiners weren't sure was brilliant or crazy, to Heisenberg on Helgoland, working through the night with hay fever, arriving at a matrix he didn't fully understand, to Schrödinger in the Alps, writing down a wave equation during a holiday with a woman whose identity we still don't know, to Bohr and Einstein, two of the greatest minds in history, arguing passionately about the nature of reality in hotel lobbies and conference halls, neither one fully right, neither one fully wrong, both pushing the other to think harder and deeper. That's the thing about quantum mechanics. It started as a desperate mathematical fix for a problem with glowing metal, and it became our deepest window into the nature of reality. It told us that the universe is stranger than anyone imagined, that particles can be in two places at once, that measuring one thing can instantly affect another across the universe, that certainty itself has limits built into the fabric of nature. And we're still figuring out what it all means. The smartest people alive are still arguing about it, still designing experiments, still building theories, still pushing the boundaries. So as you lie there, maybe starting to drift off, maybe already halfway to sleep, I want you to hold on to that thought. Not the equations, not the dates, not the names, though those are all part of the story. But the deeper thing, the idea that the universe, at its most fundamental level, is not what it seems. That reality, when you look closely enough, dissolves into probability and possibility and interference and entanglement. And that human beings, curious, stubborn, brilliant, flawed human beings, have spent the last century and a quarter slowly, painstakingly uncovering that truth, one experiment at a time, one argument at a time, one sleepless night at a time. And they're still going. Right now, tonight, somewhere in the world, someone is running an experiment, or scribbling an equation, or staring at data that doesn't quite make sense yet. And maybe, just maybe, they're about to stumble onto the next piece of the puzzle, the piece that connects quantum mechanics to gravity, or resolves the measurement problem, or reveals something about the universe that nobody has even thought to ask about yet. That's a good thought to fall asleep to, I think. The idea that the story isn't over, that the deepest questions are still open, that the universe is still out there, being strange and beautiful and waiting to be understood. And that understanding it, slowly, carefully, one step at a time, is one of the most remarkable things human beings have ever done or ever will do. So let that settle over you. Let the questions be questions. Let the mystery be a comfort, not a worry. And rest well, knowing that the universe, in all its quantum strangeness, is holding together just fine while you sleep.